Okay, let me run you through on the sphere moving through a viscous flow. So the question is set up as such. We have basically a ball going past a fluid which is viscous. Previously, we look at a ball going past fluid with zero viscosity. Now we put into more realistic scenarios. As you can see, now it's not symmetric anymore, and the flow velocity is u naught, u zero, in z direction, and the radius of the ball is a big R. And naturally, we would use spherical coordinate since it has obvious symmetry. Based on you can imagine, since every boundary conditions and all the conditions around it is a symmetry in terms of phi. So it's azimuthally symmetric. Then we can safely say that v phi is zero, because if we have any finite v phi, then it has a preferred direction, and that violates the symmetry of phi. And also we can know that Vr and v theta are phi independent. Therefore, dd phi is zero. Dd phi is always zero. And we will use that over and over again in this derivation. So first, we need to look at the Navier-Stoke equation and make it dimensionless Navier-Stoke equation. So we have the first resource is basically this is our Navier-Stoke equation. We are dealing with the steady state. So dVdt will go to zero, and we multiply the length scale and characteristic length and characteristic velocity, and we have this. We know the Reynolds number can be defined as such, and then this will be basically 1 over R naught. 1 over RE, Reynolds number. And then we multiply RE on both sides, we have this. So, and then we can change this thing to a dimensionless variable via this transformation. Basically, V star equals to V over U, P star equal, this is for low Reynolds number, this transformation, P star equals to PL over nu U, and nabla star equals L nabla, and you can find this information in the in non-dimensionalizing and scaling of Navier-Stoke equation. It's right here, and we're using creeping flow, which is a low velocity flow. Then we have this, plug everything in, and tidy it up with a little bit more algebra, and a little bit more algebra. We will find we have this expression, and for small Reynolds number, we will neglect this. So we're left with a nice expression, and bring it back to the dimensional. Is I just don't bother trying to figure out what the constant is. It doesn't matter to us for the current derivation. So we will do a curl of V, and we know that this one has a vector identity as such, And we know this is we're dealing with incompressible fluid, so this go to 0 because of incompressibility. And Laplacian can be transferred to we can use this to substitute the Laplacian, and we know that the curl of a grad equal to 0, so this thing is 0. And we know the vorticity is defined as a curl of velocity. And let's just first study the vorticity. You can check on any nodes. For me, of course, I use plasma formulary, NRL. And you just see the curl of V. Just check the formula in the spherical coordinate, and we have v phi equal to 0 and dd phi is 0. Similar here, dd phi is 0, v phi is 0. So c r and c theta is 0, and c phi is finite. We can define phi such that we have such expression, and we need to check the consistency if this is consistent with incompressibility, because we need that to be self-consistent, of course. And you can tell, like, this is pretty much the derivative. This is derivative with respect to theta. This derivative with respect to r in the spherical coordinate. And we do the we just plug in those expression into the gradient of v. Then we have the divergence of v. We have this, and we'll plug everything in, do the algebra, and also you can check on those the lecture note of all different video series in this note. I'll put in the description. And so this ended up is consistent with, because those are independent phi's. We're not dealing with some funky phi function, so this equal to this. Doesn't matter if you do r derivative is r or phi or theta. So this equal to this, so it's equal to 0. So it's subtract, so it becomes 0. Then we have met with incompressibility. We plug in the v, and then we plug the VRV theta into the with this, we plug this in again, we have this expression. So here, plug this into this, we have this after some relatively trivial algebra. And remember, we just derived from here, the curl of v is 0. Then we know that curl of v is a vorticity. So we have this expression, curl of vorticity is 0. And using this vector identity, we have this. So we know that this is 0 because vorticity is defined as a curl of velocity. Then divergence of a curl is 0. Then we're left with pretty much negative Laplacian c equal to 0. Then we know that then the Laplacian of c is equal to 0, and we know that we only have phi component, and we have it here. We plug this in, and we know the Laplacian is this, and through some through some calculation, and you know that all the others are zero, so it's relatively trivial to reach to this expression. So Laplacian, this is a Laplacian, and this is a c phi. And after some algebra, I will just be honest, it's very, very lengthy, and I don't know, and it's trivial algebra, so I think I won't show it here. And you can try to calculate. You can use, and all of those expression can be found here in the different notation. Q is pretty much the V in my derivation, and other things are pretty much the same. But mine is in more detail. But of course, it's written in LaTeX, so it's much more readable, I would assume. So where were we? We're here after we got this, and we need to solve for psi. So assume we just make a guess of psi equal to phi fr sine theta squared. We plug into equation 1, and we have this expression. And we assume this is, if you learn ordinary differential equation, this is a textbook question. You just need to plug in, just guess f equal to a Rn, and plug in. You just get n equals to -1, -1, 2, and 4. You just go through those algebra. I think it's quite in details as I show here. So we end up having this expression with four different free parameters. Then we have the psi. Now we need to plug into the definition of like VR and V theta to solve for VR and V theta. Plug in the psi here. Then we have VR and V theta. So now we need to apply VR and V theta to the boundary condition. Now we have 3, pretty much in the ball, on the surface of the ball, the VR 0, basically the flow cannot penetrating through the sphere. That's called non-penetration. And on the surface of the ball, on the theta direction, phi direction already 0, we know everywhere. Theta direction it has to be 0 because the ball is static. Then that's a non-slip boundary condition. And at infinity, the flow we would assume is at u naught z. It will flow in the same velocity, same direction at infinity. So with those 3 boundary conditions, we'll arrive to 4 equations, because it's a vector here, so we'll have 2 separate equations. So boundary condition 1, non-penetration, that's a VR here, plug in, we got equal to 0, theta doesn't matter. It's V square, it's R square. R square. And the non-slip V theta, here we have this expression, because theta doesn't matter either. Basically, we just substitute R with big R, small r with big R, and equal to 0. And then at infinity, we know that at infinity, this is 0, this is 0. Same here, this is 0, this is 0. So VR on our direction is u naught cosine theta. U naught cosine theta, and here 2c plus 2d r square cosine theta. 2c plus 2d r cosine theta. And we know that at infinity r, this will blow up, so we'll have to make d equal to 0. And by that, then we can solve for c, then c is u naught over 2. Now we look at the theta direction, then we have sine theta negative 2c plus 4dr squared. We already have c and d, but we just need to check. So here we just plug in c equal to u over 2, d equal to 0. Then we left hand side equal to right hand side. It's checked. We need to see it if it's self-consistent, and it is. Great. So now we have all 4 equations, and we have 4 unknowns, 4 equations. Then we can solve for a, b, c, d. After some relatively trivial algebra, we have this a, b, and c, d. So we have finally the velocity flow. This is the velocity flow, and you can check back to the MIT derivation they have, and they have it somewhere. There we go. Yeah. And now it doesn't let me move. Great. Okay. So now let's look at the pressure. We know from the dimensional Navier-Stoke equation, we know that essentially this is gone, we don't consider gravity, then we have basically those 2 terms in Navier-Stoke equation. And we just need to substitute v into this expression, and through some nasty algebra, we have Laplacian in the r direction, and dpdr. We just basically substitute vr and v theta into this expression, and use the Laplacian and some identities you can find anywhere pretty much, and I find it on NRL plasma formulary. That's, every plasma physicist have one, at least one. So after some algebra, you can try to follow it yourself. I don't think it's worthwhile me just showing it the algebra, talk through the algebra. I think I put it pretty extensively through here. So Laplacian of v on r direction is Laplacian vr and that. And we know that is phi independent, so we have this. So we plug in, this is the Laplacian. This is basically this is this, and this is this, and we have here and here. Let's just put an x, and this is here, and this, let's put a check. This is this. So this is v theta, and this is VR. And then we do some algebra. This is basically checking on here, and this is here. This is this. So we have this, and ended up, thankfully, we have most of them cancels out. We have this expression, nice expression, and then this is dpdr, and we integrated on r. So we're just, and it's pretty trivial integral. Then we have this. We have this pressure. Thankfully, we got that. and we know that is azimuthally symmetric, then you can intuitively think that it's pretty much the pressure will contribute it to only z direction. So let's just see the like an element of the like a force due to the pressure. So it's basically the pressure at z multiplied by the area through the z direction. So we know that z can be expressed in terms of r hat and theta hat. We have this, and ds we have this expression. And then just put everything in. We have this nice little expression. And this ds, is basically basic element d theta r d theta and sine theta. That's a two line element, right? D phi. That's a ds. And all the surface element is on the r direction, because on the surface is always radial in the sphere. So we do the integral through phi and theta. We know it's azimuthally symmetric, so we just have 2 pi here, and substitute the p we just calculated right here, and we have this nice expression. Through this calculation, this is a relatively trivial integral done in calculus. I don't bother doing it. I just do it through honestly Mathematica. And we have this, and substitute it in. We have this expression. And I think it's 2 pi. Yeah, it's 2 pi r mu Sorry, I need to check on something. So negative 2 pi r mu u naught z. So it's opposite of where the flow comes from. Is, of course, it should be. So for viscous, for the viscous stress tensor, you can check on the Wikipedia. There is really good documentations, but for what we care is pretty much the spherical fluid dynamic, like fluid equation in spherical coordinate, and we have nice note from Dr. Fitzpatrick. And but so we have, what we care about is r theta and r theta, sigma r theta r, and if you follows through this in terms of derivation of Stokes drag, then you will find this nice expression. I find it's easier to calculate basically compact the VR theta over R. I mean, Dr. Fitzpatrick have 3 terms, but for our case, it's easier that way for us. So we just use this just use this expression. It's the same equivalent, and we just substitute VR and V theta, and then I have this expression, and a lot of them cancels out. We ended up have this expression for sigma R theta, sigma theta R. Similar to calculating the force on due to the pressure, we can calculate the force due to the stress. But the stress is in theta direction. So we just start on theta direction is will be negative, then we have d theta sine theta square r d theta d phi sigma r theta. Similar drill to the force due to pressure. We just do the integral through Mathematica, or if you want to do it by hand, go ahead. So we have this expression. Then we now have force due to pressure and force due to stress. Then we add them together, we got the drag, and it's called Stokes drag. And that's pretty much it. To cap, we make a dimensionless Navier-Stoke equation, and you can check them on Wikipedia. Basic everywhere it has a link, you can click on them, and then we do some algebra on the tensor analysis using some vector identities, and then we look at the vorticity, and then we define, without losing at the consistency, we define the VR V theta as such and plug them in. We find that incompressibility works for them, and then we plug the velocity into the vorticity using we discover the vorticity is this, and then after some algebra, have differential equations, solve for a differential equation, and apply the boundary condition, non-penetration, non-slip, and also at infinity we have u not at z equals z, and then we solve for the boundary condition, got all the free parameters set, got this velocity, calculate via the dimensional Navier-Stoke equation, and we got the pressure, and then we integrate through the surface, got the force due to the pressure, we got the stress tensor, we got the definition from Dr. Fitzpatrick, and plug in VR V theta, and we got this, and then we integrate similar to force due to pressure, we got force due to stress, add force due to pressure and stress, then we got drag, which is Stokes drag.